It's my great pleasure to have this opportunity to speak in this wonderful conference. In my talk, I will give deformation point of view for my recent joint work with Xiaowu Chen on a description of singularity categories via DG Leavitt path algebras. So the talk has 3 parts. In the first part, I give a motivation to the result. And in the second part, I will state our main result. And in the last part, I will give an explicit example. So yeah, first, let me remind you the main object of this talk, namely the singularity category of a finite dimensional K algebra A. So this is just a bounded derived category of finite generated A modules quotient by the perfect derived category of A. So this means this the for subcategory formed by the complexes of quasi-isomorphic to bounded complex of finitely generated projective A modules. So this notion was introduced by Bookwise in 1986, and then it discovered by Orloff in 2003. So yeah, the singularity category is 0 if and only if by definition this if only if the 2 categories coincide, and if only if the global dimension of A is finite. And for self-injective algebra, this algebra the singularity category has a nice description by the stable module category of finite generated A modules. Okay. And our motivation is the following theorem by Smith in 2012 and by Chen-Yang in 2015. So we consider a finite quiver Q tutor, and then we look at the associated radical square 0 algebra of Q tutor. So namely, yeah, this is just the path algebra quotient by the radical square, and then by the yeah, as a vector space is just isomorphic to this algebra is spanned by the vertices and arrows or in Q tutor. Okay, and then the singularity category of this algebra has nice description by, namely, yeah, it can be described by the perfect derived category of some GG algebra trivial differential. So namely, LQ tutor is a graded Leavitt path algebra. So yeah, here is the definition. So first we look at the double quiver of Q tutor. So namely for each arrow in Q tutor, we add the opposite arrow. Okay, even for loops, we add the new loop. And the quotient by then we look at the path algebra of this double quiver and quotient by the two-sided idea generated by the following 2 types of relations. So the first relation means the new arrow is the right inverse of the old one. Like we have alpha star equals it's just equal to the vertex. But in general, this one is this new arrow is not the left inverse because yeah, we have this relation. Okay, so for each vertex here, we consider the all the arrows start sorry, for each vertex we consider all the arrows starting from this vertex, and then we look at this element and take the sum. Okay, so yeah, this algebra is you can it's actually a universal localization of the path algebra. Okay, by inverting some morphisms between projective modules. Yeah, here is the example. So we look at the following quiver Q tutor. So here we have 2 vertices and 2 loops, and also 2 arrows between them. And then the double quiver is the following one. So we add a new arrow for each arrow in Q tutor. Okay. So we know, then we look at the radical square 0 algebra, so which is a 6-dimensional, because yeah, here we have 2 vertices and 4 arrows. And then the Leavitt path algebra is given by the path algebra of the double quiver and the quotient by these relations. Okay. And later I will give another 6-dimensional algebra, which is a symmetric algebra. And yeah, we will see. Okay. So now there is a natural question. So can we generalize this result to for any finite dimensional algebra of this form KQ mod I? So here I is a two-sided admissible two-sided ideal. Okay. And yeah, here I would like to share you how we thought about this problem. So yeah, here's the idea. So first, we have the following fact, which goes back to Sharps in 1988. So namely, any finite dimension algebra can be viewed as a deformation of some radical square zero algebra for some quiver Q tutor. Okay. So by this I mean this algebra A can be isomorphic to the radical square zero algebra, but with perturbed multiplication here by some molecular element. So somehow we have to change the multiplication here by this element. So this element is in degree 2 of Hawkshead-Coaching complex. So by molecular element I mean this algebra satisfy these equations. Okay. Here this one is the Gesthaber bracket in Hawkshead-Coaching complex. This equation is equivalent to seeing this algebra. Okay, it's associative. Okay, that's it. And later then recently with Xiaowu Chen and Huang Li, we construct a natural morphism of DG Lie algebras for any radical square zero algebra. So namely, we have a morphism of DG Lie algebras for the Hawkshead-Coaching complex of this radical square zero algebra to the Hawkshead-Coaching complex of the Leavitt-Pass algebra associated to this quiver Q tutor. Okay, and then by the general fact of morphism of DG Lie algebras, we know this map send the molecular element mu to a molecular element here. Okay, so in general, the molecular element gives us an infinity structure. So namely, the molecular element has a many components, like and this for any I big to equal to 0. But here we are lucky because for this one we only get one component, namely all the components are zeros except I equals 1. Sorry, I equals 1. So then this means we get a differential on this algebra. Okay, so this just means we only get the DG algebra, not A infinity algebra with high non-trivial Hyatt structures. Okay. Let me give you some remarks about this map. So actually, this map can be extended into a B infinity morphism. So because both sides have a higher structures, so we can make sure this phi can compatible with the higher structures. This actually also factors through another coaching complex which computes the singular Hawkshead cohomology or Tate Hawkshead cohomology, and also about the differential. So the differential is can be constructed in another way, which is closely related to a box theory. Okay, so namely you can construct this D from a different point of view. Okay, good. And now we can state our main result. So as we discussed, we start with the algebra A, and then we construct the a radical square zero algebra, and this A can be viewed as a deformation of this radical square zero algebra by the molecular element mu. And from this mu, we can transfer this. Mu using the DG Lie algebra morphism to get a differential or molecular element on this Leavitt-Pass algebra. So namely, we get this DG Leavitt-Pass algebra. So this is also a deformation of this graded Leavitt-Pass algebra. So then there is a natural question. So can we lift this triangle equivalence to a triangle equivalence here between the deformations? So then our main result is give a positive answer to this question mark. So namely we have a triangle equivalence between them. But the proof is not, we don't give a purely deformation theoretical proof. Our proof relies on new DG enhancement of the singularity category. So this is the so-called, we call singular unit DG category. And this category satisfies the following relation. Like if we compute the DG and the morphism algebra of the simples of A, then yeah, this DG algebra is precise isomorphic to the DG Leavitt haphazard algebra. So in this way, we know by the general result of Keller, we know, then we can get this result, this triangle equivalence. And Keller with Wang, they proved a different proof using so-called derived localizations in the sense of Brown-Chang-Lazarev. So namely, this DG algebra is intrinsic, namely it's a derived localization of the Kuzu dual of A. Okay, so yeah, this means this DG algebra is very natural. Okay. Okay, and then at the end I will give you an example. So we look at another 6-dimensional algebra here.
Zhengfang, maybe 1 minute.
Okay, 1 minute. Okay, thank you. So this is a 6-dimensional algebra, and we know this algebra is a deformation of the previous one. So this is the radical square 0 one. Okay, so yeah, let me recall you this quiver we have seen before. And why this? Because they have the same dimension. We can fix a morphism of like a k-linear space. So which send vertices to vertices, and and send arrows to this arrow to this arrow. Okay, and it loops to some non-zero composition of arrows. Okay, and then we can also get the molecular element mu by transferring the multiplication here to here. Okay, so then we get this one, and which is given by this the following assignment. Okay, and then using this mu, we can construct a differential. Okay, we can compute this using the morphism or using box theory. Okay, so we have different ways to construct this, and then at the end we have this DG Leavitt haphazard algebra. Okay, so this we have a C, and the differential is generated is given by looking at the action on arrows. Okay, so for all other arrows we take to be 0. Okay, and then we get this triangle equivalence. Okay, then thank you.